Today I want to present you a real life case where we use the liquid lenses and the simulation capabilities of Zemax to solve a real problem, in particular a problem in the healthcare sector. Before starting, I want to present you a bit Optotune for those that might not know the company. Our company has two main expertise topics. One is optics, in general lenses, but also other optical components like mirrors, prisms, diffusers. We work around all of them. Next to it, our other expertise is actuators. The most used is voice coil actuators, but we also know how to use reluctance force actuators, electroactive polymers, and most recently we have incorporated shape memory alloys. With all this, our customers can benefit of optical components that give them very compact designs, increase the flexibility of how to generate these designs. Also, we have components with higher speeds and long lifetimes. The product we will talk today about is the liquid lenses, one of our main products. And the liquid lenses solve one of the problems that is most important in optics, and it's changing the focus. For a long time, the solution that engineers have found is based on big glass elements that need to be very precisely fabricated, very precisely aligned, and that need to be moved with regard to each other. This is a very complex solution and presents a lot of trouble in terms of tolerances and fabrication. And if we compare to nature's solution is much simpler. It just the eye, it's a ball full of liquid. This ball is flexible, and our muscles are able to press and change the curvature of the frontal surface such that the rays of light coming from different distances can all be focused at the same point in our retina. And this is exactly what Optotune has been able to copy. The liquid lenses that Optotune have developed mimic the principle of the nature's eye by using membranes and liquids and allow to focus the light to different distances in a very fast movement. As I said before, these lenses give more compact designs for the optics, have a very fast response that is also very reliable and precise. And also because there are less parts in these lenses, the sensitivity to tolerance is much lower than in the complex optical designs. Finally, because these lenses are excited electrically, they can be controlled remotely, which is also another advantage for our customers. But let's stop talking about Optotune and let's go to the real case. Today I want to talk about skin melanoma. It's summer, it's arriving, we all like to be tan and we all go to the beach and spend a lot of hours in the sun to get that nice color of skin. However, we all know that this is not without risk. We need to protect our skin, and even when we do so, there are cases where we can get skin cancer. In particular, skin melanoma is a very important type of skin cancer. It happens when the melanocytes, which are the cells that give us this nice color, start to grow out of control. The first symptoms that we could detect would be a mole that changes in size or in color, or some unusual stains and pigmentation that would appear in our skin. Most of these cases of skin melanoma, estimated at 3/4 of the cases, can be attributed to the UV radiation. That means the sun, the radiation, or that radiation coming from artificial sources like the sunbeds. This type of skin cancer accounts for around 1/5 of all the skin cancers. And that might look like it's not much, but it is called sometimes the most serious type of skin cancer. The reason behind that is that even if at the first stages is very mild and it's only some moles growing a bit more than we would like, the cells from these moles can get to the bloodstream or to the lymphatic system and can allow the cancer to spread to other organs of our body. When that's the case, the rates of survival of this cancer can go very lower. In Western countries, skin melanoma rates are increasing a lot. That's because populations that before were not exposed to sun and artificial UV sources now are increasing that exposure. In particular, in the European Union and the US, it's now the 6th most common cancer by number of cases. It represents about 4 or 5% of all the cancer cases that are detected every year. Globally, every year we have more than 300,000 new cases of skin melanoma. And as I said before, prevention is of course the first step that we should take, but the second one is detecting it earlier. Because this cancer has this initial state where it can be removed just with small surgical intervention, it's important that we detect the cancer very early in the stages. Otherwise, the cancer can spread to the whole body and it becomes much more complex. It's because of this that the European Union is funding the project iToBoS in the program Horizon 2020. And this project is devoted to generate a tool that will allow for this early detection of skin cancer. The name iToBoS comes from Intelligent Total Body Scanner, and the main objectives of this project are the following. First of all, there is a hardware objective, which is building a new scanner that is able to take pictures of the whole body of the patient. The second objective is creating an artificial intelligence assistant that will take these pictures of the skin of the patient and will mix this data with other sources of medical data from the patient. Genomic data, medical records, family records. With all this information together, the artificial intelligence assistant will be able to give a diagnostic to the physician that is much more accurate and takes into account many more factors. Another thing that we want to do in this project is to be able to compare images and data from different visits. As we said, skin melanoma is characterized by the change of these moles, the change of these stains in our skin. Because of that, it's important that the system is able to compare pictures from one visit to the next one and see the evolution of those moles, or even detect new moles that are changing. Finally, one problem of artificial intelligence diagnostics is that in general, they give a black box answer that has no reasoning behind. In the iToBoS projects, we want to implement what is called explainable AI. Explainable AI is a type of answer that also highlights what part of the data that we gave to the system has been used to reach the conclusion or the diagnostic that is given as an answer. This is very important for the physicians such that they can take this answer as another data point for their decision with reason behind that and not just as a blindfold answer from a machine. Finally, the last two objectives, it's about testing the system in real life. First of all, we will be taking lots of pictures from real patients such that we can build what is called the ground truth for these systems. Artificial intelligence systems need a lot of data to be trained such that the answers start to be reliable. So that's one of the things that we will do within the project. And finally, we will be testing the new technology in 3 hospitals that are part of the project in Barcelona, Trieste, and Brisbane. As you can imagine, Optotune as a hardware company will be working on the creation of this new body scanner. The body scanner will be based around a bed where the patient will be lying, and around the patient there will be 5 arches. Each one of these arches will feature 3 camera modules that will be able to move laterally and vertically such that they can cover the whole surface of the patient's body. And finally, each one of these modules will have a high resolution camera because we want to be able to have images that give enough detail to the doctors to see all the features of the mole. We'll have an objective lens. This will be Optotune's part because the distance between the camera and the patient will be quite high, so we'll need to focus to where the skin of the patient is. We'll have a lighting system such that we have control conditions and all the pictures are comparable. And finally, we'll have a distance sensor such that these pictures can be located in an avatar that the doctor will be able to look, zoom, and use to understand exactly where each mole is, how it has evolved, etc. Going even one step further, when we look up close to the optical module, we need to fulfill several conditions. The first one is safety. Of course, this device needs to be safe for the patient, and that gives us a very important constraint, and is the distance between the patient and the camera. There is a lot of regulation around how these machines can be built, but in summary, what we have is that the camera and the optics will be around half a meter from the patient. The second constraint is comfort. We all have had some MRI, which is a very uncomfortable test because the patient needs to be a long time, 10-15 minutes, in a small space with a lot of noise. In this case, one of the goals is to minimize the time of the scanner, so being able to take all the necessary pictures in the minimum amount of time. The third of the constraints is that we want high-resolution images. Until now, the better images that a physician can use come from a handheld dermatoscope, which is a small machine that the doctor can approach to the skin of the patient. In that case, the camera and the optical system are just 1 or 2 centimeters from the skin of the patient, which means that they can take very high resolution images. In our case, as we already said, the camera will be at more or less half meter from the patient. So if we want high resolution images, what we will get is a very small field of view, or what is the same, very small area per each one of the images. The last of the constraints is the fact that we are imaging a 3D object, our body. What happens with this is that we are at a long distance, we are having high resolution, but high resolution is only obtained with a small focus of our image. And that also means that we can only focus to a very small depth of field. Because of that, and to be able to have good resolution, good focus on all areas of the skin, we will be using what is called image stacking. As you can see in this scheme, what we will do is take several images, just moving the focus a small amount of distance every time. And in the end, we will combine all those images, taking the parts of each image that is in focus in each one of them. This way, we will create what is called a hyper-resolution image, which will have all the points, no matter what is the depth, in high resolution, in high focus. Because of all these constraints, in the end, what we find is that we will have to make thousands of pictures, small field of view, image stacking, we need a lot of pictures, and at the same time, we want to take them in the minimal amount of time. And that's what brought us to the use of the liquid lenses from Optotune. As you might already know, our lenses can change focus in a matter of few milliseconds. In the case of the EL1640, our biggest lens that we have chosen for this project, the time that we need is 12.5 milliseconds to be stable in the next focal power. Compared with mechanical optical systems, this is really fast and will allow us to reduce the time needed for all these images to the minimum. The last thing that we needed to do before starting the design was to understand exactly what are the requirements for the objective lens that we have to design. Our liquid lenses have some range of focal power, but because we will be at a big distance from the patient, we'll need some standard glass optics around it. To find these requirements, the first thing that we did was taking pictures of real moles, real patients, in different optical conditions, different lighting, different distances, different apertures. With this, we could show these pictures to the doctors, and they were able to tell us in which pictures they were seeing enough detail for them to understand if that mole was dangerous or not. But of course, that's only half of the work, because with this qualitative statement from the doctors, we cannot design a system. We need some quantitative specifications. The second step was taking images from some standard targets, in our case, the US AFA targets. These kind of targets have very well-defined patterns from which we know exactly the sizes, the separation. With these two pairs of images, we could compare the images that the doctors told us that have enough detail to understand if a mole was dangerous or not, and calculate which are the specifications needed from the USF target image. Doing so, we were able to prepare a set of requirements that we wanted to use for the further design. Here we can see working distance. We already discussed about that. In the end, we fix it as at 42 centimeters from the patient. We also had chosen the camera. In the end, we chose a big format camera with 1-inch sensor. We decided what was the resolution that we needed in the object, 20 lines per millimeter. And also another important parameter, we decided what was the MTF, so the contrast that we wanted in the images in different parts of the sensor and with different resolutions. With all these requirements, we could already start our design.
Now let's take a look at the design of the body scanner camera that is using a liquid lens inside. Here you can see the layout with a couple of performance characteristics of this lens. Noteworthy is the location of the aperture stop, which is pretty much at the front, and its size is very comparable to the image circle of the image sensor, which has a diameter of 16 millimeters. You also see that there's a field of view, a diagonal full field of view of 12 degrees. So it's an extremely tele-like camera, which comes from the fact, as Xavi has elaborated before, that the camera needs to be placed at a rather far distance from the patient for the comfort of it, but still needs to be able to image very small details with a very high precision. So that's the reason why this is a very tele and a narrow field of view camera. It has f number of 4 and an effective focal length in the order of 75 millimeters. The total length of the design is 95 millimeters, and you can also see here in this layout from Optic Studio the location of the liquid lens. It's ranging from here to here, and it's represented by the following surfaces. We have like an outer housing surface that is indicating the location of the envelope and the diameter. Then as a next element, we have the container glass, then we have the liquid compartment, then we have the membrane, a cover glass, and on the other side again we have some an indication of the housing in terms of location and diameter. What we are using here, as was mentioned before, is an EL1640 TC lens, which seems to be very suitable for the case, especially in terms of the clear aperture. The term TC refers to a feature of some Optotune lenses, which is called thermally calibrated. That means these lenses are not only calibrated in terms of focal power versus drive current when they are undergo the final test at Optotune, but this is also repeated at several temperatures in order to get a full thermal drift compensation of these lenses. And this is happening by the means of a temperature sensor, which is on the lens, and also an EEPROM for data storage. So all the data that is acquired in this multi-temperature calibration procedure is stored on the sensor and is automatically compensating for focus drifts, which are a result of temperature changes. And the two mechanisms that come into play here is, first of all, the change in refractive index with a change in temperature that is common to all optical materials like plastics, glasses, and also these optical liquids, but they are stronger here with these optical liquids. And the other effect is the thermal expansion. So all the materials are expanding or contracting when the temperature is changing. And also these changes are compensated automatically by these liquid lenses. Now, on the right-hand side, you can also get an impression of the optomechanical design that surrounds this optical layout. You can see there's a stack of glass lenses that are inserted in a lens barrel from two sides. These lenses are not visible here because they're black boxed. And then you see the location of the liquid lens here with a yellow frame, and the liquid lens is actuated via an industrial grade high rose cable that you see on top here. We are at the end of our webinar. What we have seen in the first part with Xavi, that apart from prevention, the best way to fight skin melanoma is by detecting it very early. And this is the goal of this EU project iToBoS. And it's a big project with different research sites being present or being included. And it's a great thing here to be able to work on this project as Optotune and being able to contribute